Hello, everyone. My name is Daniel, and together with Jefferson, we are going to present now the work titled Blockchain Privacy Through Merge Avoidance and Mixing Services. This is a joint work between Federal University of Rio de Janeiro and UniRio. The main motivation for our work is concerns related to privacy and anonymity in crypto systems. Recently, the IRS offered a 625,000 bounty to anyone who can break Monero and Lightning, indicating that such problems are indeed tough, the problem of breaking anonymity. But at the same time, another group says that IRS should study those cryptocurrencies rather than just trying to break it. And that's precisely the goal of this paper, to study the extent and the hardness of implementing robustness in a scalable fashion. The cryptocurrency ecosystem involves both cryptocurrencies that have low privacy level, such as Bitcoin and Ethereum, and other cryptocurrencies that offer higher levels of privacy, such as Monero and Zcash. The first sort of cryptocurrencies, they tend to be preferred by governments in order to track users, and the second one by those users that set privacy at premium. Our work fits in the first category, as we are going to discuss additional strategies to increase the privacy in the first case. There are at least two types of linkage in financial systems that users of those crypto systems want to avoid. Linkage between wallets from same user and linkage between users through shared coins. In the first case, the hackers want to determine that two virtual wallets are from the same user, whereas in the second case, hackers may want to determine that a given coin was transferred through a given path. Whereas in the first case, we have different coins shared by a same user. In the second coin, we have the same coin, but that is transferred through multiple users. And the solution to avoid the linkage between wallets from the same user is to avoid this merge of wallets in single transactions, to keep the wallet split across transactions. Whereas for the second one, to avoid the linkage between users through shared coins, the solution is to mix those coins through mixing services. And these are the two main subjects of this work. Now, getting a bit more into the details of those two strategies, merge avoidance and mixing services, both aim at obfuscating the network by adding transactions. Whereas the first relies on the server and receiver for that goal, the second relies on the network of users, including relays, to obfuscate the network. And our contributions are to show that merge avoidance involves an NP hard in one version of the problem, and mixing services involve incentive compatibility issues which may be impossible to be addressed if we want to be at the same time incentive compatible for senders and relays. Now we are ready to move to the first part of our main results, which pertains merge avoidance being NP hard. Merge avoidance was first proposed in 2013, and it was then discussed in multiple contexts, including in the context of CoinJoin in 2017, and the linkage between wallets was also explored in tools such as BitIodin in 2014. But the theory that we are going to leverage in order to discuss the hardness of merge avoidance dates back to the 70s. And in the theory of computation, there is a long-lasting history of coin exchange problems, which may be referred to as the Frobenius coin exchange problem or the subset sum problem. And our contribution here is to relate those problems to anonymity issues. So our goal is to transform a transaction graph so that no two transactions merge together. The produced graph should have the minimum number of edges, and the constraint is that the inputs and outputs should be preserved. So for instance, in this graph here, we have 3 inputs, 2, 4, and 3, and 2 outputs, 5 and 4. The sum of the inputs equals the sum of the outputs, and we want to produce a new graph where the inputs and the outputs are preserved and avoiding the merge. In this case, the solution is trivial because we can transfer 2 units from the wallet A to wallet D1 and 3 units from wallet C to wallet D2, where wallets D1 and D2 are virtual wallets associated to the previous wallet D, and the additional 4 units from B are transferred to E, and in that way we satisfy the constraint while minimizing the number of transactions that we have in the produced graph. Now, main theorem in this part states that the multi-target merge avoidance, which is the problem that I just described, is NP-hard, and the proof simply follows from a reduction from the partition problem. We consider a transaction with multiple inputs and 2 outputs, and if we are able to divide these input values into 2 groups, where these 2 groups correspond to the 2 output values, then clearly we can solve the partition problem using the optimal merge avoidance as a function. So this is the main idea of the reduction. And interestingly, we also show that in another version of the problem, where we distinguish the exchange transaction, things become much easier. A simple extension, which may look subtle, actually completely change the landscape. So we show that if we change the constraint, now assuming that we have a typical transaction which involves only 2 outputs, a target value and an exchange, and the only constraint is that we have to produce a new set of transactions without merges, preserving the target output value, but having the exchange being arbitrary, then we actually can verify that this single target merge avoidance problem can be solved through a greedy polynomial algorithm, which simply selects the topmost inputs to meet the target, assuming the inputs are ordered based on their values. So these are the main ideas from the merge avoidance, and now we are ready to switch to mixing services.
So let me talk a little bit about the idea that we're trying to portray here on mixing services. So the fundamental idea here is that we want to conceal the identity of a node that's taking part in a certain operation. And the way that we achieve this is by performing this operation through a sequence of proxy nodes. So the original idea came from these web anonymity services or systems, especially Tor, which became quite famous several years ago, where instead of accessing directly a website, you route that request through a number of nodes, and they are going to reroute back the response from the server. So essentially, that original identity of the node that requested the website first is not exactly lost on the process, but it is concealed through this sequence of relays. And the idea here is to apply that same idea to operations involving cryptocurrencies and so forth. So we're going to call this original node the applicant node, and the remaining nodes are going to be called here for our purposes of this work are going to be called concealment nodes. And all of these nodes, they constitute a concealment route which will be used to hide the identity of the applicant node, right? So one problem in putting this idea in practice is that we require the proxy nodes, which are part of the normal or usual cryptocurrency system. We require them to behave selflessly and act in order to help uh, another node in the network, and usually in order for this to scale when you don't have control over the nodes that are part of your system, and whether they are going to want to behave in the selfless fashion, you need to include in your system an incentive of some sort, so they are interested in, or they become interested in helping other nodes. And our focus on this work here is going to be on systems uh, that incentivize its participants through credits that are actually paid by the applicant node, which is uh, getting the benefits of the mixing service process. And we're going to take a look into one particularly kind of incentive, which is a zero-sum credit system. That is, everything that the source pays up for using this mixing service is going to be redistributed and paid back as a reward to the proxy nodes that took part on this process. So no currency or no credit is lost on the process. And this credit could be the cryptocurrency itself, or could be another kind of credit of some sort. And the question we want to address here is, can the nodes that participate in this routing process, in this mixing service, either the concealment nodes or the applicant node itself, can they take advantage of this reward system and gather additional rewards that they were not entitled to through the process itself? That's the question we want to address here. And we're going to look at a particular kind of attack, which is called an edge insertion attack. This attack, it came to be in the literature of packet routing in networks, particularly DTN networks and some papers in D2D networks, and where you require the nodes in your network to help other nodes to forward their messages or their packets. And the edge insertion attack consists in falsely claiming that additional nodes took part in the forwarding process, or in our case here, the mixing service process, in order to collect the awards these additional nodes would be awarded, would receive on their behalf. So this is not a really huge problem if you can validate the process, the route itself, using some kind of centralized infrastructure, some server that authenticates each and every node in the process. But if you want to do that in a distributed fashion, and that's in particular the case of cryptocurrency systems or any blockchain services, this becomes quite a challenge because you don't have this infrastructure. So one way to use or to skew the reward system is, in order to attack this problem, in order to tackle this problem, is to try to discourage the edge insertion attacks by paying smaller and smaller rewards as your route gets longer. So even if a node tries to perform this attack, the total reward it gets for it is still smaller than the original quota it would receive if it hadn't performed the attack. So that's the kind of strategy we're talking here about. The issue here is that the edge insertion attacks can also be performed by the applicant node itself. In this case, it's not like it's going to get more rewards than it was entitled to, but instead it will recover a part of its own cost in the form of these rewards to falsely existent nodes in the path, in the route that was performed. That how can we can balance these two issues. That's the challenge here. And what we show actually is an impossibility result. The idea is that actually we can't prevent these two kinds of attacks by the applicant node and by concealment nodes in a single zero-sum credit-based identity concealment process. Uh, if this process follows two rather simple assumptions, which are that all nodes involved in the routing process, in the mixing service process, they receive equal rewards, which is a property we call uniformity, and also that the credits that are paid to each node don't depend on anything else other than the length of the route itself. So we just count the number of nodes that acted as proxies, and that's going to depend how much credit each one is going to receive. Right? This we call in our work we call this length dependency. So the fundamental reason for this impossibility process is that each kind of attack requires a kind of dependency between the route length and the individual reward value, and the functions resulting from this dependency, they are fundamentally irreconcilable. So for the applicant node to be disincentivized to perform this kind of attack, we need a reward that is non-decreasing with the route length. But for this process to be disincentivized for the concealment nodes, the reward has to be decreasing with the attack level, that is, with the number of false Sybil nodes that you add to the route. And this decrease has to be at least inversely proportional to the level of the attack. And naturally, these are two conditions that are impossible to satisfy at the same time. All right, so just for a final discussion on this last problem, there's a fundamental assumption here is that we assume that both attacks, both kinds of attack by an applicant node or by a concealment node are actually feasible goals and design of the system itself. And in certain situations, it might be the case that these attacks are not practically feasible to be performed. For example, if in a situation where you determine the route through which the identity is going to be concealed through beforehand, it would be impossible to simply deviate from this process or from this sequence of proxy nodes, since eventually some node in the process will not be able to decrypt the message and perform its part in the process. So these are some issues that need to be taken care of, and then can actually be an alternative to these other possible solutions to the problem that we just mentioned. And this has to be designed in a case-by-case basis, essentially depending on the protocol, on the conditions that you have for the cryptocurrency system itself. So with that brief discussion, I'm going to end our presentation, and I thank you very much for your attention.
Thank you very much.